today's question is a bit different than the regular questions you'd expect. So it's the float fill. Let's go through by reading the question first. So as an input, you get an image, m times n. And inside that image, every pixel represents a value for an image. Yeah. And you're also given SR and SC, which is basically a row and a column point, and a new color. And you should perform a float fill on the images starting from pixel that we will get as an input. And here we get more of a constraints what you should do. So basically, to perform a float fill, consider starting pixel plus any pixel connected 4 directionally to the starting pixel. If it has the same color, then we do it, otherwise not. And we should replace it with a new color. So as you can tell, the question is not so clear, so I will try to make it an easy explanation. If you can see now the iPad, so here is the input, what you get on the left. And basically as an input, you'd see we have here a grid, which is representing an image, and every point in that grid is basically a pixel on that image. And the value that we have here is the color of that image. So for example, here pixel 00 has 1, pixel 01 has 1, pixel 02, sorry, 00, 01, 02 has a value of 1, and so forth. So this is a grid, basically R times C. So just to make it easy here, so this is the R, and this is the C. So here's the column, basically column 0, column 1, and column 2. And likely here we have row 0, row 1, and row 2. And as an input, you get the value here. So in that case, for example, you get a pixel, as you see here, R1 and RC, and you get a color. So let's get back to here. So as an input to the question, we got this value here, which is 1 and 1, and we get a color of 2. And basically what we're allowed to do, or sorry, what we should do, is that we come here, so that's the pixel that we start with, and that's the color that we want to paint. And you see, okay, if this pixel has any neighbors 4 direction basically means if it shares, if it's across the axis, the x-axis or the y-axis, so not diagonally. So here on that axis, basically, what I'm drawing now, this is basically the 4 directionally connected. So in that case, this pixel here is connected with this one here. It's also connected with this one here, with this one here, with this one here. And what you should do is, once you get this input and the color, you should paint it, that's one, and then you check every neighboring pixel if it had the same value, and if it has the same value, you also paint it or change the color. And you do the same for at every step. So for example, let's walk through it here like step by step. So this is the input, and we say color 2. What we do first, we just change this value to be 2. Okay, we make it 2. And then we check, okay, what are my neighbors here? So what neighbors that have the same color as I had, the old color. We check here, okay, this value is a neighbor and it has the same color. This value is a neighbor and it has the same color. Then I go again and basically do the same. I change this value to be 2, which is the new color. And then at this step here, I check, okay, what are my neighbors on the X and the Y, and do they have the same color as I do? And yes, they have I have 2 neighbors here, this one here and this one here, and they have the same color, the 1. So again, I go there and I change that to be 2 and here to be 2. Likely I go here and then I try, okay, what are my neighbors? And it will be this one here, which I already seen before, but let's do it again. So I just make this 2, and then I go at that square here and check, okay, who are my neighbors that have the same old color I had, the 1. So I'll find that this one here. So I go to this pixel, I check, do I have any neighbors that have the same color and they are on the x-axis or the y-axis? No. So again, I changed this one here. So if you notice, these are the pixels that are relevant in that question. This one here, this one here, this one here, this one here, and this one here. And this is what you see. So we change the values of these pixels, the neighboring. And you notice, I mean, if you pay attention here, you would notice that we did not change the pixel here, even though it has the same color, but this is because it's not four-directionally connected. It's a diagonal. There's no X or Y connection to it. That's why it stayed the same. So that's the problem. As an input, I will show you the input like how it is code-wise. So the input, you get a 2D array, which is the same as the one here. You get the source row and the source column, and you get a new color. And output, you should return the output array after you modify it. So this is easy, but it's not really, so it's simple, yeah, but it's it's a bit tricky to get the answer. So you can just think right away, if you're gonna do the same step more and more and more, then this is a recursive by default. And I'll show you what I did here, and I will also explain how it goes. So basically, this is derived from the same solution that we discussed here. That at every step, we do the same thing. We check the neighbors, the X and the Y neighbors, and we change the color of the current pixel. And again, so checking the neighbors, we check that they're 1, we change the color. Then we check the neighbors, change the color. Check the neighbor, change the color. Change the neighbor, change the color. So that's what we do in short. And from here, we came up with this solution. So let me try to explain it. So this is the input method here. And as an input, we get the image, we get the source row, source column, and we get the new color. What I did, it's simply a recursive function. So remember, we only change the color if it was, if it's different, yeah? So that's why I have this condition here. I check, okay, is the colors different? Because if it's not, assume that you get the same one and it's again a 1, so you don't need to do the recursive call over and over, so you just return the image as it is. If it's a different color, then here goes the funny part, or the fun part. So the recursive call, what it does exactly as we said here in English. So we start with it, and then let's see, what's our base case, okay? Base case will be if the grid that we have, the value of the row does not exist, yeah, or if the value of the, so like row doesn't exist, meaning for example you get an outbound, yeah, you get an index which is not even in the grid, or it's a pixel that's undefined. That also means that the C is undefined, so you can have a row here but it's an outbound C, outbound column, so it's the same as the first one, but one is checking for the row, one is checking for the column, and we check if the pixel have a different color than the original one, so it's not a 1, for example, in here, then we don't do anything. And of course we have this one which I did to optimize it. We basically have a visited node, and this is keeping track of any nodes that we have visited. So what you see here is just a combo of row and column, and we add this to the list of visited nodes, so we don't need to do the recalculation twice. It also helps with optimizing the recursion function. And if any of these cases happen, what we want to do is just return. We want to do nothing. Otherwise, which means the pixel is there, it's a valid point on the grid. It means also, yeah, that it has a different color also. Sorry, it has the same color as the original starting pixel. Then what I want to do is I want to first change the color. Yeah, so here I change the color to be of that pixel to be of the new color. I want to add it to the visited node, so I remember that I added this, that I visited this, and then we basically go through all its 4 directional neighbors. So this is calling the same function again recursively, but with different rows and different columns. So if you go again to the iPad here, at every step basically, let's clean this up if we can. I hope we do. Yeah. Yeah. So here, at every pixel, so just assume that you start here, this position. You start here. What you want to check? You want to check this pixel here. You want to check this pixel here, this pixel here, and this pixel here. So if we go from left to right, like if we were to go clockwise, we found that this one is basically, so assuming this is the column and here is the row. I hope it's throwing. Okay, here's the row and here's the column. So this pixel here, let's call this 1 and this 2 and this is 3 and this is 4. So pixel 1 is basically at position the same row, yeah? So it's the same row, but it's the previous column, so it's C minus 1. Pixel 2, this one here, it's basically the same column but different row. So it's the row above, which is R minus 1. Pixel 3 is the same row but different column. And pixel 4 is the same column but different row. So these are the 4 places where we want to check. Yeah. And this is what we do exactly here. So if you look here, this is what we do here. We go through these pixels and we do the same thing. We just pass the visit node and we expect it to do the same logic again. It goes there, it checks every pixel. Is it valid pixel? Is it having different color than the original, or it's visited before? Then I ignore it. Otherwise, I change the color and then add it to visited nodes and call its neighbors, call the same recursively on its neighbors. And this is what we do here. So that's the basic solution that I have. And if you check the submissions, it also worked. Let's try to analyze now so let's first of all try to describe it in English, what we've done here to make it easy. So basically in English, what we do at every pixel, yeah, we want to check if the pixel color is the same as the original pixel color. If yes, change the color and check all its 4 neighbors. That's it. That's basically what we do in plain English. Of course, there are some optimizations, as I said, with visited nodes array, and the other cases we check it's not out of bounds, but this is exactly what we do. So let's try to check the time complexity. So the time complexity, we have to go through every pixel. Yeah. So let's check the amount of pixels that we have. So the pixels we have is basically R times C. So the time complexity will be O. Let's not put here. Big O of R, which is the number of rows times the R number of columns. That's what we do. And space complexity, we have a visited node, which is basically the full size of the grid. And we also have the recursive stack space. So I would go with the same also as here. So that's the time complexity and that's the space complexity of such solution. I hope it was clear, and waiting or looking forward for our next lesson.